So moving on, if it's not a power model, it could be an exponential model. So when an association follows an exponential model, the transformation to achieve linearity is carried out by taking the logarithm of only the response variable. So it still involves a log, that transformation property, but this time we're going to only take the log of the response variable, and that's to kind of get rid of the exponent, or get the variable out of the exponent. So if a variable grows exponentially, its logarithm of that variable should grow linearly. So if you have a variable, if you have data that is growing exponentially, population growth or population decay is a great example of this. It's probably our most common. Any kind of population, bacteria, people, whatever, typically grows exponentially. That's probably our most common example, but there could be other situations as well. So this is looking at college students collected data on the intensity of light. So light intensity is on the y-axis versus at various depths on the x-axis. So the scatter plot is showing kind of the depth versus light intensity, and then this bottom one is showing the depth versus the log, or in this case ln, so the natural log of light intensity. So we can kind of see that that scatter plot that has the log of intensity versus depth is much more linear, almost exactly perfectly linear. Here's some computer output from that linear regression model. Again, depth is still depth, like the x variable is the same. What changed is we now are dealing with the log, or the natural log in this case, of the y's. In terms of log versus natural log, that shouldn't matter a lot. Just in this specific example, it does specifically say that they used natural log. So when I write my equation, my y, which was light intensity, is now going to be ln of light intensity, or log, natural log, because that's what they used, is equal to, again, I'm using my same form of an equation, so my constant is my y-intercept, 6.789. My slope is now negative, so minus 0.333 times depth. So we did not take the log of depth, we just took it of the intensity. And then I can use that equation again to find predictions. So it's similar, and this should be predicted values. It's similar to what I did with the power model in terms of how I use it to solve. So my ln of intensity, which is what I'm solving for, and that's a predicted value, is going to be 6.789 minus 0.333, and I'm doing a depth of 12 meters. So obviously on the right side, that's all numbers, so I can put that in my calculator real quick, which I will do. And that gives me 2.793. And then because this is a natural log, it is base e, so to get rid of the ln, I'm going to do e to the on both sides. That will make that cancel. So I have predicted intensity is equal to e to the 2.793, which is 16.33. And I don't remember what the lumens, the light intensity unit. So same idea, just different form of an equation, and I can use that to kind of still write an equation and still make predictions, even though the data was not linear. So then it comes to, like, how do I know which model to use? We've seen power models, we've seen exponential models. How do I know which one is an appropriate transformation? So the good news is that none of this is stuff that you're going to have to kind of come up with on your own. We haven't seen questions on AP Test where you have to actually build the model yourself in a long time. But you may be given situations where they give you output from both types of models or different models, and you're trying to determine which one's best. So if you're not sure which transformation is best, the two things we want to look at are first the residual plot to see which one has the most random scatter, the least amount of curved pattern. So that's always what we want to look in a residual plot. And the second thing you can look at if you have multiple residual plots that are very similar is that you can look at which model gives you the highest R-squared value. So this is looking at braking distance or stopping distance for a car, which is the amount of distance a car takes before it can come to a complete stop. Less is better. Researchers collected data on the braking distance measured in car lengths for a car making a panic stop in standing water, along with the tread depth of the tires. So following is a linear regression. The tread depth is in 1/32 of an inch units. So following is a linear output for 3 different models. So when I look at that, this is my original model, just using the braking distance and the tread depth. So just using the original variables. This was my residual. So I can see that very curved pattern in the residual, which would tell us that this model is probably not great. Then I have a model where we did the natural log of braking distance and the natural log of tread depth. So this would be that power model. So I can see that this one, there's a little bit better in terms of residual plot. I don't see as much of a pattern or barely any of one at all. And then I have model 3, which did the natural log of braking distance only versus tread depth. So this would be that exponential model. We just take a log of the y's. And I can see that there's also a very clear curved pattern there. So it seems like our best bet would be this model 2. Now, if we had 2 residual plots that looked very, very similar, what I would want to look at then is the R-squared value. So I can kind of see this one's 0.822, this one's 0.999, that one's 0.886. So even the R-squares is telling me that this model 2 is the best one. So in terms of which model does the best job, we would say model 2 for 2 reasons. Its residual plot has the best random scatter. There's the least amount of pattern in that residual plot. It's still not perfect. We still see maybe a little bit of a curve right here, but it's the least amount of pattern. And then the second reason would be we see that R-squared value is the highest. So that's another reason we would want to pick that model. So once we've got that model, we're going to use it to calculate and interpret a residual. Remember, residual is the difference between observed and predicted y. So that would include 2 things. I would first need to find the predicted y variable, and then I would need to subtract. So to find that model, I'm going to first go back to this and use this information right here to write an equation. So I have the ln, or natural log of braking distance, I'll just put distance predicted, is equal to 2.9 minus 0.27 times the natural log of tread depth. So that's my equation I'm going to use. So now I'm going to use that and kind of plug in. So first I'm going to find a predicted distance. So using that tread depth of 3/32 of an inch, remember our tread depth they told us was in units of 1/32 of an inch. So in this case, I'm just going to plug in a 3. So 2.9 minus 0.27 times the natural log of 3 would give us our natural log of distance. That's what I'm solving for. Again, everything on the right side I can put in my calculator, which I will. So that would give me ln of distance equals, that's about 2.603. And then I'm going to do my trick where I'm going to do e to the, since that's a natural log, it needs an e base. That will cancel that out, and I'll be left with predicted distance is equal to e to the 2.603, which is 13.5. So that is my predicted distance, and they didn't ask us for predicted, they asked for the residual. So my residual is the observed y variable, which was 13.6. That's what actually happened for this car, minus our prediction, which is 13.5, gives us a residual of 0.1 car lengths. And interpreting that is the same way we've interpreted residuals in the past. I would say that this car's actual stopping distance was 0.1 car lengths greater than what the model predicted based on their tread depth. And that is how we can kind of choose the best model and make a prediction from it. So in terms of what I didn't realize I put that there. That would have been helpful. So in terms of what you will be expected with this unit, I know that's a lot of information and it's a lot of algebra. So if it's the algebra you need help with, make sure you either get with a friend or come see me. But in terms of the statistics part of it, it's just really recognizing that that residual plot and that R-squared value are important in determining what model is going to be the best. So those are the things we wanted to remember and know. A lot of this particular lesson we don't tend to see as much on AP tests. So felt like it was a good one to do while I was away. All right.